Okay, let me show you the contents of this video tutorial which I'm going to cover. First, I will talk about what is the need of the state space. For that, I will compare the classical and modern approach of system modeling. Then I will talk about the introduction to the state space system modeling. Then I will explain few basic definitions such as state variables, system state, state vector, and the state space. After that, I will talk about the state space modeling of some physical systems such as mechanical and electrical systems. And then I will talk about the state space to transfer function conversion and vice versa. And in the last, I will talk about one MATLAB code that is used for state space modeling of a physical system and its some basic analysis. So let's go ahead. But before going ahead, I recommend you to watch following my video, that is the LTI system analyzer using MATLAB GUI. Although this video is not directly related with the current tutorial, but if you go through this video, you will learn the basics of the LTI systems. So this video you can find at link which is given in the description. So now let's start the topic. So first I will compare the classical and the modern approach of the system modeling. So the classical approach of the system design is based on the transfer function, while the modern approach of system design is based on the state space. The transfer function approach can be used to model the systems which are linear and the time invariant, I mean the LTI systems only, while the state space approach can be applied to non-linear, time varying systems, and it can be applied to LTI systems also. The classical approach doesn't consider any initial conditions in the system, while state space based modern approach considers all the initial conditions of the systems. The transfer function based classical approach can be applied to the single input single output systems which are known as the SISO systems, while the state space based modern approach can be applied to the multi input multi output systems which are known as the MIMO systems. It is also applicable to the SISO systems. The transfer function based approach is frequency domain approach which works with the Laplace transform, while the state space based approach is the time domain approach which doesn't require any Laplace transform. So it is very difficult to handle the complex systems in this approach, while this approach can well handle the systems with the complexity. So that's why the state space based modern approach is preferred for modeling the various practical systems, because it considers all the initial conditions and it is applicable to the linear, non-linear, time varying and time invariance, all types of systems. So now let's see how a system is represented in state space. So let's consider the following MIMO system as shown below. So the UT is the input for this system and YT is the corresponding output. XT actually are the chosen state variables. Later I will talk about what are these state variables. Since this is MIMO system, so UT is not a single input. Let me consider there are R number of total inputs from U1 to UR. And similarly, the outputs are total M outputs from Y1 to YM. And the chosen these state variables are N number of state variables from X1 to Xn. And then this system can be represented by the following two equations which are also known as the state equations. So the first equation is this, the d by dt of the xt is your the state variables, axt plus but, and the second equation is yt equal to cx plus dut. So these two equations are actually the representation of any system in the state space domain. For simplicity, sometimes we omit this t variable. So in compact form, we write these two equations as x dot equal to ax plus bu, y equal to cx plus du. In this pair of equations, as we have just seen, all the symbols are actually the matrices. Okay, so the actual representation follows like this. So this simple equation, which is x dot equal to ax plus bu, has the actual representation like this. It's a matrix differential equation. So the d by dt of all the state variables. So since we have the n number of state variables, so this is n by 1 matrix. Again, it's all state variables are here. So again, it's a column matrix n by 1, and this is the A matrix whose size is n by n. Similarly, we have the R number of inputs. So this is the column matrix R by 1 size, and this is the B matrix whose size is n by R. Similarly, I can write this output equation y equal to cx plus du. So since I have the m number of outputs, that's why it is a column matrix of m by 1 size. These are state variables x1 to xn, so this is n by 1 because number of state variables are n. That's why the size of this C matrix is m by n. And here again I have the R number of inputs, so it's a column matrix of R by 1 size, and this is the D matrix whose size is m by R. Here these A, B, C, D matrices have their names. So this A matrix is known as the state matrix, the B matrix is known as the input matrix, this C matrix is known as the output matrix, and this D matrix is known as the direct transmission matrix. So now let's come to some basic definitions which are required to understand the state space modeling. So first, let's see what are the state variables. Actually, the state variables of a dynamic system are the least number of the variables that are required to completely describe the behavior of the system. So if some input ut is applied at some time, let's say t equal to t0, and initial conditions are known, then with help of these variables we can predict the future response of the system. So you can clearly understand that this is the least number of variables chosen for a particular system, such that they are able to completely describe the behavior of a system. So now consider one example of an electrical system. So for electrical system, a simple rule is that we consider the inductor currents and the capacitor voltages as the state variables. So now consider this simple series RLC electrical system where we will consider the inductor current and the capacitor voltage as a state variables, and these are sufficient to describe this electrical system completely. So in this case, you can see that I is your inductor current. So one state variable, let's say x1, that is equal to I mean the inductor current, and the second state variable x2 is equivalent to the capacitor voltage, that is E naught. So only these two state variables are sufficient to describe this system's behavior. Now let's come to the system state. So what is the system state? The state of the dynamic system is the smallest set of these variables, so-called state variables. So in the previous case, we have seen that we have selected, let's say, least number of state variables, and then set of these variables is known as a system state. So for example, for the same RLC circuit shown below, the state of the system is represented by this set of state variables. So we have already chosen these two state variables, inductor current and the capacitor voltage. So if I arrange them in a set, this is represented by xt. So xt is known as the system state. Okay, so it is known as a system state. Now let's see what is the state vector. So if I choose the n state variables for a particular physical system, and if I assume that all these state variables are components of a vector, then this will become the n-dimensional vector, and it is known as a state vector. So you can see that here this state vector xt bar is represented like this: a x1, b x2 plus cx3 till xn. Here your x1, x2, x3 all are state variables. Okay, so if they are arranged like this in this algebraic sum format, they are representing actually one state vector. So for RLC circuit as shown below, we can write the state vector. Okay, so as we have already chosen the inductor current and the capacitor voltage, as the state variables. So I can write the state vector for this electrical system. So from this equation you can see that xt equal to ax1 plus bx2, right? So since I have only the two state variables, so my state vector will be represented by only the two components. So that's why I'm writing xt bar equal to ai, because x1, the first state variable is the inductor current, and then second state variable is the capacitor voltage. So this is how I can represent the state vector for this electrical system. Obviously it is a two-dimensional state vector, okay. And now let's see what is the state space. So the n-dimensional state vector definitely will create the n-dimensional state space, okay, in which it can be represented. Similarly, if you have the three state variables x1, x2, x3, it can be represented in a three-dimensional space. So let's consider this RLC circuit again. So in this RLC circuit, we have chosen only the two state variables. One is the inductor current I and the capacitor voltage E naught. So these two state variables actually making this state vector which has only the two components. So that's why it is creating this two-dimensional space. Okay, so one is the current axis and other is the capacitor voltage axis. So this two-dimensional space is created by the two state variables, and this space is known as the state space. Okay, and inside this space, any point like this is actually representing the system state xt at some time, let's say t equal to tf. So if the point is at the origin, how you will define the system state? Obviously, if the system state is at the origin, it means at that time the capacitor voltage and the inductor currents both are 0. I mean, your system state is 0, 0 at this point. So when you apply some input, obviously the current will change, the voltage will change, so your point will move to some final direction or to final state with respect to the time. So as time elapses, this state will move to some final state, let's say. That's why I have written that this is the state at t equal to tf, and this is the initial state at t equal to t0. So you can see that by changing the input, the system state is moving only on this two-dimensional space. Okay, so here the same thing I have written, that any state can be represented by a point in this state space. So now let's consider one more example where I have taken the three-dimensional space. So consider this electrical network. It has the two inductors L1 and L2. So you have the two currents IL1 and IL2 to select as the state variables. Similarly, you have one capacitor. So the capacitor voltage VCT will be chosen as the state variable. So total state variables for this network are three: IL1, IL2 and the VC. So obviously, since these are three state variables, so definitely they will create the three-dimensional space like this. Okay, so you can see that one axis is IL1, one other axis is IL2, and the third axis is the capacitor voltage VCT. So what is this red dot? So this red dot is actually representing the system state at some time t. So whenever you give input, okay, so obviously these currents and voltages will change, and this point will move in this three-dimensional state where as time elapses. So at this origin, this is the system state at t equal to t0. Okay, at t equal to t0. So here all the state variables are 0. Okay, so all the inductor currents are 0, capacitor voltages are 0 if the system state is at origin. So that's why it is known as the initial state. And when we give input, some input VIT, obviously these currents will change, capacitor voltage will change. That's why this system state is moving in this three-dimensional space. So now you can understand that what is the system state and what is the state space. Now let's come to the modeling of the physical systems, how we can represent the physical systems in state space. So first consider this example of a mechanical system. So here I have considered one spring mass damper mechanical system. So a force ut is applied downwards to this mass m, and the yt is the corresponding displacement. So now consider the free body diagram for this mass. So you can consider this mass m, and all the forces are shown here. So the ut, that is the external force, it is applied fu downward, and because of it the spring is stretched, so it is pulling up this mass. So that's why this fk is upward. This damper is compressed, so it is pushing up this m upward. So that's why this is the damper force. And since movement is downward, so inertial force will be upward, that is Fi. So by simply considering the force equilibrium, I can write force equation as Fu. So Fu is only the downward and all other forces are upward. So Fu equal to Fi plus Fe plus Fk. So that is the force equation for this system. And now I can write these forces. So Fi is simply the mass into acceleration. So since displacement is y, so y dot is velocity. So displacement is y dot is velocity, and y double dot will be acceleration. So here you can see that my double dot means it is the second derivative. Okay, so it is d square upon dt square yt. So that is the acceleration, and plus damper force actually is proportional to the velocity. So b into y dot t. Y dot means it is the first derivative of displacement. So that is the velocity. And the spring force, you know, it is simply the spring constant into the displacement. So spring constant k multiplied with the displacement yt, and applied force is ut. So thus this equation is converted into this differential equation. And for simplicity, I can omit this t variable. So my equation is written as my double dot plus by dot plus ky equal to u. Okay, so let me rewrite this equation. So for this mechanical system, I obtained this differential equation. And this differential equation can be easily converted into the equivalent state space model. Let's see how. So for that, first I have to choose the state variables. So here I am choosing the first state variable as a displacement. So that's why let's say x1 is the first state variable, which is equivalent to the displacement, and the second state variable is equivalent to the velocity. So I can write these two equations. So x1 equal to y, that means displacement is the first state variable, and the second state variable is actually your velocity. Okay, the simple rule is that by the order of the differential equations, you can have idea about the number of state variables to be chosen. It's a second order equation, so obviously two state variables are sufficient. Now I have to rewrite this equation 1 in terms of only the state variables. So for that it is easy. See, y double dot is actually the x2 dot. How? This is y dot, so y double dot will be the x2 dot, so that is written, and by dot, so y dot is simply x2, and ky, and y is simply x1, so that's why x1 is written here. So this equation 1 is converted into this equation where all the variables are the state variables. So from this equation I can write these equations, keeping differential term to the left and taking all the variables to the right side. So I get this equation 4, and now let me rewrite these equations, equation 3 and equation 4. So from these two equations 3 and 4 I can write the state equations. Let's see how. Okay, so the first equation or the first line of this matrix equation, you can see that x1 dot equal to x2, x1 dot equal to x2. So same I have written x1 dot equal to x2. It is 0 because 0 is multiplied with the x1. So it will vanish. 0 multiplied with u, it is vanished. So only relationship is x1 dot equal to x2. So x1 dot equal to 1 multiplied with x2, it is simply x2. Now the second, this fourth equation can be written as a second line here. So you can see that x2 dot equal to minus k upon m x1. So this is k upon m x1 minus b upon m x2 and 1 upon m u. Okay, so this is how I could write this state equation, and that is your first equation. That is equivalent to the x dot. So this is x dot equal to ax plus bu. So this is your A matrix and this is the B matrix for this mechanical system. Now let me write the output equation. So output equation can be simply written because I have already considered y equal to x1. So this equation is represented by this matrix multiplication. So y equal to simply x1. 1 is multiplied with x1, 0 multiplied with x2. So that is representing the same thing, y equal to x1. So this is my second equation, y equal to cx plus du. So this is my C matrix. Okay, and this is x and d is not here. So obviously d is 0 in this case. So this is how you can see that these two equations actually representing my mechanical system in the state space. Now let me consider another example of electrical system. So consider the series RLC circuit. Here I have to represent this electrical series RLC network into the state space. So for that, again I have to choose the state variables. So as I already said, for electrical networks you have to choose the inductor current and the capacitor voltage as the state variables. So in this case the inductor current is I and the capacitor voltage is Vc. So you can see that there are only the two state variables Vc and I for this system. So I can write the KVL in this loop. So this is the KVL L di by dt, so that is the voltage across inductor, plus IR, voltage across resistance, and voltage across capacitor is 1 upon C integral I dt equal to the input voltage Vi. So it's a simple KVL. But consider one thing, because I have to write the state equation. So in the state equation there is no integral term. Okay, so I have to remove it. How I can remove it? Simply, instead of writing 1 upon C integral I dt, I will simply write Vc in place of it. Okay, so in this equation now you can see that there is no integration term. And one thing you have to keep remember, that whenever you are writing differential equations for some system, keep this in mind, that there should be one differential term. Okay, there should be one di by dt term, and there should be and the second thing is that all the variables must be the state variables. The remaining variable must be the state variables or the input variables. Okay, so whenever you are writing the differential equation, you have to convert in this format. I mean, there should be only the one d by dt, and the remaining terms should be either state variables or the input variables or both. So if you see this equation, it satisfies both the requirements. I mean, it has one d by dt term, and see all other variables. This is I, which is also a state variable. Vc, it is also a state variable, and the Vi, that is the input variable. So this equation is satisfying these two conditions. I mean, one d by dt term and the remaining variables must be either input variables or the state variables. So from this equation I can write in this format, di by dt equal to minus r upon li minus 1 upon l vc plus 1 upon l vi. I mean, keeping the d by dt term to the left and taking all the terms to the right side. So this is my equation 1. And for this capacitor I can write this current voltage equation. So I equal to C dvc upon dt. So from this equation I can write dvc by dt I upon C. Now consider this equation also, whether it is satisfying these two requirements. Yes, it has only one d by dt term, and all other variables are your state variables, I mean I. So from equation 1 and 2, I can write the state equations. So let me rewrite these two equations again. So from these two equations, I can write the state equations like this. Okay, so d by dt of Vc and I. So I'm writing the second equation as the first line. So d by dt of Vc is simply I by C, I mean 1 upon C into I. So I is written here. So that's why 1 upon C is here. 0 multiplied with the Vc. So no relation with the Vc and only relationship with the I. 1 upon C, and there is no Vi term, so it is 0. Now the equation 1 is entered at the second line. So d by dt of I, so d by dt of I equal to minus R by Li. So minus R by Li minus 1 upon L Vc plus 1 upon L Vi. Okay. So the equation 2 is entered at the, equation 1 is entered at the second line of this equation. So this is my x dot equal to Ax plus Bu. So this is matrix A and this is matrix B, which I have achieved. So very simple. Now I can write the output equation. In this case, the output of the system is the capacitor voltage itself. So obviously the Vc equal to Vc. So Vc equal to Vc. So here I am writing Vc equal to 10 Vc into I. So that is equivalent to your Cx plus du, y equal to Cx plus du. So this is your C matrix, D is missing here, so D is 0. So this is how I can represent my any electrical system into the corresponding state space. Now consider another example, example 3. Consider this network. It has actually the two inductors, L1 and L2, and one capacitor. So as I suggested that how many state variable you have to choose? Obviously 3 state variables. I mean the inductor currents and the capacitor voltage. So first inductor, the current is I1, and for second inductor current is I2, and the capacitor voltage is Vc. So my state variables are I1, I2 and Vc in this case. So this system has 3 state variables. Now let me write the KVL for the first loop. So L1 di1 by dt is this voltage across inductor, then R I1 minus I2, I mean voltage across R, and that is equivalent to the input voltage Vi. So that is KVL in the first loop. Okay, from this now I can write the KVL in the second loop. So that is plus minus this drop, that is L2 di2 by dt, and this drop voltage across R, that is R I2 minus I1, and then plus Vc equal to 0. There is no external source in this loop, so that is it is equal to the 0. So I have written these two equations. Also in the second loop you can write the voltage and current relationship for this capacitor. So I2C, so this is your capacitor current, so I2 equal to C dVc by dt. Okay, so that is equation 3. So I have written these 3 differential equations for this circuit, and let me rewrite these 3 equations again. So from these equations 1, 2 and 3, I have just kept this derivative part to the left side in all, and then transferring all the terms to the right side. Now consider that required condition which I have just explained in the previous case. What was that condition? The condition is that in all these equations there must be only one d by dt term. Okay, so this is satisfying, it is also satisfying, it is also satisfying. They all have the 1 d by dt term. Also the second condition was that the remaining all other terms must be either source, input source, or the state variables. So see this first equation here, I1, that is also a state variable, I2, it is also state variable, and Vi is the input source. So the equation 4 is satisfying both the two conditions. Similarly here, I1, I2, Vc all are state variables, so it is also satisfying those conditions. And the sixth equation, it is also satisfying the same condition because only one d by dt term and the remaining variable is I2, that is a state variable. So now from these equations 4, 5 and 6, I can write the following state equations. Okay, so the first equation, I mean the fourth equation, is at the first line. So d by dt of I1 equal to minus r upon L 1 I1 plus r upon L L1 I2 and 1 upon L Vi, 1 upon L Vi. Okay, similarly the second equation, d by d2 of I2, that is r upon L2 I1 minus r upon L2 I2 and minus 1 upon L2 Vc. It has no input Vi term, so it is 0. And in third equation, d by dt of Vc, d by dt of Vc equal to only 1 upon C I2. So it is related with the only the second term I2. So 1 upon C, all other terms are 0. So this is how I could achieve this x dot equal to Ax plus Bu. So this is my A matrix and this is my B matrix. Similarly, I can write the output equation. In output, the capacitor voltage itself is the output. So that's why again Vc equal to Vc. So same is written here. So Vc equal to Vc. So this is how I could achieve both the state equations, x1 dot equal to Ax plus Bu and y equal to Cx plus Du for this electrical network. Now let me consider one more electrical circuit. It is slightly complex. This is a network, and here you can see that I have only the two elements which will provide me the two state variables, this inductor and this capacitor. So inductor current, that is equal to I1, and the capacitor voltage, that is Vc. So only the two state variables sufficient for this network. And now let me write some differential equations. So first I will write the KVL in the loop 2. I mean in this second loop I am writing this KVL. So obviously this V2 equal to Vc plus V0. V0 actually the R into I1 plus I2. Both the currents are actually going inside this R. So they are additive. Okay, I1 and I2. So this branch is taking I1 plus I2. So this R into I1 plus I2 you can see. So this plus Vc equal to V2. So that is KVL in second loop. Also in this second loop, this I2 equal to C dVc by dt. So that is a current voltage relationship for this capacitor. So this is my equation 2. And now substitute I2 in the above equation. I mean substitute second in the first. Why I'm doing this? Because again consider those requirements, two requirements which I just suggested in the previous slide, that you must have one d by dt term. So if you see the equation 1, there is no d by dt term, right? Second, there must be all variables which are either input variables or the state variable. So in this equation, I1 is the state variable, Vc is the state variable, V2 is the source, but I2 is not state variable. Okay, so if I substitute I2 from this second equation, my I2 will be replaced, and also from this d by dt of Vc, I will get the first derivative term also. So after substitution, I get this, and now you can see this equation. I have one d by dt term, and all other remaining variables are either input or state variable. So this is the required equation from which I can write the state equation. So from this equation, keeping d by dt Vc to the left and taking all other terms to the right side, I will get this equation 3. So from this equation 3, I can directly write the state equation. But the first loop is remaining. So let me write the KVL for the first loop also. So writing the KVL in the first loop, this is the equation. So this is the voltage drop, that is R into I1 plus I2, because the central branch is taking both the current I1 and I2, plus this drop, that is the L di1 by dt, and it is equivalent to this supply voltage V1. So this is this differential equation for the loop 1, or just by opening it, this equation becomes this. L di1 by dt plus Ri1 plus Ri2 equal to V1. Now let me check again those two conditions, that it should have only the 1 d by dt term. Yes, it has only the 1 d by dt term. And second is that all other variables must be the state variables or input. So let's check. V1 is the source, okay. I1 is the state variable, but what is about this? I2 is not state variable. So to satisfy the second condition, I have to replace I2. So in such a way that I should get, or I should satisfy those two conditions. So let me how to replace this I2. So from equation 1, now consider the equation 1 again. So let me show you the equation 1. So this is the equation 1. So equation 1 is Ri1 plus Ri2 plus Vc equal to V2. So obviously you are getting Ri2 term here. So from this equation 1, you can replace Ri2 by the remaining variables. So the same thing I am doing here. So from equation 1, I am getting this Ri2 term. So Ri2 equal to simply V2 minus Vc minus Ri1. So I can substitute this Ri2 here. So when I substitute Ri2, I will get this equation. So L di1 by dt, it's same term, Ri1, it is same, and in place of Ri2, I am getting these three terms, that is the V2, Vc, I1R, and then equal to V1. But here you can see that Ri1 and minus Ri1 both are same but in opposite sign, so they will be cancelled out, and the remaining equation is L di1 by dt plus V2 minus Vc equal to V1. So now again let's check those two requirements, that it has only 1 d by dt term. Second, all the remaining variables are state variables or the source. So here V2 is the source, V1 is the source, and Vc is the state variable. So now this equation is satisfying those two conditions. So from this equation, keeping d by dt to the left, taking all terms to the right, I get this equation 5. So now I can write the state equation. So from equation 3 and 5, again let me rewrite them. So from these equations, I can write the state equations like this. So from equation 3, I can write this second line. So d by dt of Vc minus 1 upon C I1 minus 1 upon C I1 minus 1 upon RC Vc minus 1 upon RC Vc, and V2 1 upon RC. So V2 1 upon RC. And from fifth equation, I can write d by dt of I1 1 upon L Vc. So Vc is this. So this is 1 upon L Vc. No term of I1, so it is 0. 1 upon L V1, 1 upon L V1, and then minus 1 upon L V2 minus 1 upon L V2. So from equation 3 and 5, I can write this equation. So that is x dot equal to x plus bu. So this is my A matrix, this is my B matrix, okay. And now let me write the output equation. So output, what is the output? If you have seen the circuit, you can see that this output is represented across this resistance, that is V0. So I mean the voltage across resistance is the output. So V0, the expression of the V0 is actually R into I1 plus I2. So that I can again achieve from the equation 1. Okay, so from equation 1 I can write again, I mean, or you can simply write KVL in the second loop, KVL in loop 2. You can write V0. So V0 equal to simply V2 minus Vc. So I can write this in matrix form. So here you can see that V0 equal to V2 minus Vc. So V0 equal to, it is not related with I1, so 0, and minus Vc. So that's why minus 1 Vc, and V2 is there. So it is not related with the V1, so 0, and with V2 it is 1. So this equation V2 minus V1 is written in this matrix form. So this is the second state equation, that is y equal to Cx plus du. So this is your C matrix, and this is the D matrix. So first time you can see that you have achieved the D matrix. In the previous two examples, the D actually we obtained 0. So here we obtained all the four matrices A, B, C and D. So these are few examples of physical systems, that how you can convert them into their equivalent state space model. Okay. So now let me explain you what is the relationship between the state space and the transfer function. Okay. Actually, as I said, that LTI systems can be modeled by transfer function and they can be modeled by the state space also. So LTI system has both representation, the classical approach, I mean the transfer function representation, and the modern representation, that is the state space representation. So therefore, there is a direct relationship between the transfer function and the state space model of the same LTI system. So the TF model, I mean the transfer function model of that system, can be converted into the equivalent state space, and the state space model of that same LTI can be converted to its equivalent transfer function. I mean that interconversion is possible. So you can see how it is possible. So you have this LTI system. So via modern approach, it is represented by the state space. The same LTI system in classical theory is represented by the transfer function. So we have the interconversion. So I mean you can convert this state space into equivalent transfer function, or you can convert this transfer function into the equivalent state space. So in the coming section, I will show you that how you can do this interconversion. So first we will see that how you can convert the state space into the transfer function. So now consider these two state equations. So let's say my system is described by these two equations. So to represent that system into the equivalent transfer function, first we have to take the Laplace transform of equation 1. So when I take Laplace transform, there's x dot, that is the derivative of x. Obviously it is sxs minus x0, where x0 is the initial condition, and axs plus bu as. So that is the Laplace domain representation of equation 1. But for finding transfer function, by the classical theory we know that for transfer function you have to neglect all initial conditions. So you have to make x0 equal to 0. So by doing this, you can take axs to the left side, taking xs common, you will get Si minus A equal to BUS. What is I? I is actually the identity matrix. Since S is a single quantity and A is a matrix, so you cannot subtract, okay, a matrix from a single quantity. So the S is made matrix. So your actually Si is your S00 S matrix. So you are subtracting A from it and BUS. So now take this Si minus A to the right side, you get xs equal to Si minus A inverse. So it will become inverse into BUS. Okay. So let's say this is equation 3. Now take the Laplace of the second equation. I mean this. So you have the Ys equal to Cxs plus Dus. Now what you have to do, you have to substitute this xs here in this output equation. So we will substitute equation 3 into equation 4. So by that substitution I get this. So y is equal to c, and this was your xs. So I have substituted the value of xs, that is Si minus A inverse BUS plus DUS. From here you can take u common. So the remaining part is only this. So now take us to the left side. So this becomes ys upon us equal to c Si minus A inverse into B plus D. So obviously this is the relationship of ABCD matrices. That means the state space model of that LTI system with its transfer function. So ys upon us is actually the transfer function of the system. So this equation 5 is representing the relationship, or you can say the conversion from state space to transfer function. Now let me take one example of this theory. So consider this one LTI system which is represented by these two state equation. So this is your A matrix, this is B matrix, this is C matrix, and D is not present, so D is 0. Now your question is how to represent or convert this state space into the equivalent transfer function. So you will use the relationship which we have just derived. So y is upon us equal to C Si minus A inverse into B plus D. So substitute all ABCD matrices in this relationship and do that mathematical operation. So I have put all these equations. So C, this is C matrix, this is Si minus A inverse of it, this is B matrix, and D is 0. Okay, and you just subtract this. So S 0 minus 1 minus 1, 0 minus 5 minus 5 plus 5, S minus minus 2, S plus 2, like that. So now I have to find the inverse of this matrix, and since it is a 2 by 2 matrix, the inverse is very easy. In 2 by 2 matrix, you just exchange this diagonal and invert the sign of this diagonal and divide it by the determinant. Okay, so that is a simple method to find the inverse of 2 by 2 matrix. So here you can see that I have exchanged this diagonal. So S plus 2 here, S is here, and I have inverted the signs of this diagonal. So minus 1 to plus 1, plus 5 to minus 5. Okay, and then this is the determinant. So S into S plus 2 minus 1 into minus 5. So that is plus 5. So it is a determinant. And now I have to multiply these three matrices. The denominator is already there, and I will get this. So this is the output, or you can say that this is the transfer function which I have obtained from that state space model of that LTI system. So this is very simple example. So now you can convert any ABCD state space model into its corresponding transfer function with this simple formula. Okay, now let me come to the reverse operation. So reverse operation means now I will convert the transfer function into the state space. So I'm taking the first example. So consider this case. It is the transfer function, that is 1 upon s square plus 2s plus 5. So if you want to represent this transfer function into the equivalent state space, it is very easy. You just do the cross multiplication. So when you do the cross multiplication, you get this, and obviously take ys inside. So s square ys plus 2s ys plus 5 ys equal to us, and now take the Laplace inverse of this equation. So when you take Laplace inverse s square, definitely you will get the second derivative y double dot plus 2y dot plus 5y equal to u. So this equation is converted into the time domain. So it is a simple differential equation, and from this differential equation you can write the corresponding state space in the similar way what you have done in the case of that mechanical system. So it becomes very easy. So first you have to select the state variables. Since it's a second order system, so you have to choose the two state variables. So let me, y is my first state variable and the y dot is my second state variable. So let's say this is equation 3, and now I can represent the equation 1 into state variables only. Okay, so you can see that y double dot is simply x2 dot, and y dot equal to x2, y is simply x1, and u is u. So this is my equation which is now converted fully into the state variables. So let's say equation 4. So with help of the equation 2, 3 and 4, I can write the state equations. So I have rewritten these equations now, equation 2, 3 and 4. So this is how I can write this equation, x dot equal to x plus bu. So x1 dot, okay, so x1 dot equal to x2, so x1 dot equal to x2, 0 and 1. Okay, and this fourth equation x2 dot equal to minus 5x1 minus 2x2 plus u, so 1u. So this is how I could write x dot equal to ax plus bu. So this is A matrix, this is B matrix. Now I can write the output equation. So output equation is easy. So y equal to x1 only. So y equal to x1. So y equal to x1. No relationship with this x2, that's why it is 0. So this is a y equal to cx plus du. So this is the C matrix. D is not here. So this is how you can convert any transfer function into the equivalent state space. Okay. So this is the example 1. Now consider the example 2. So this is my transfer function y is upon us equal to s plus 3 upon s square plus 2s plus 5. So what is the difference between this example and the previous example 1? The difference is that in previous example the numerator was only the 1. So that was 1 upon s square plus 2s plus 5. But here the numerator is now one polynomial of s. So that previous method is not applicable here, because if you do the cross multiplication, you will get s into us. So s into us means by taking Laplace inverse, you will get the d by dt of ut. So that will be the derivative of the input. But as you know that there is no d by dt of input in any of the state equation. So obviously this method won't work. So what I have to do? I have to separate actually the numerator polynomial and the denominator polynomial like this. So introducing one more variable, let's say vs. So I can write ys upon vs and vs upon us, because vs can be cancelled out. So it's the same thing, ys upon us. Okay. So it will not change your equation, and you have separated the numerator and the denominator polynomial. Now what you have to do? You have to equate the numerator polynomial always with the output variable ys and the denominator polynomial with input variable us. So this is how I could separate these two polynomials, I mean the numerator and the denominator polynomial of s. So this is my equation 1 and this is my equation 2. So now you can understand why I have done this. If you see this second equation, here you are getting us and you are getting 1 here, which is similar to your previous example. So now if you do the cross multiplication, you will not get any the d by dt term of input. That's why this separation is done. So now consider the second part and now do the cross multiplication. So this is simply cross multiplication and taking Laplace inverse. So when you take Laplace inverse, this equation s square vs means v double dot, 2svs means 2v dot plus 5v equal to u. So this is a simple differential equation, and from this differential equation you can get your state model in a similar way what you have done in the previous example. So it's a second order, so you have to select two state variable. So let's say the first one x1 is v and the x2 is the v dot. So with help of these two equations, I can convert the equation 3 in terms of state variables only. Okay, so v double dot. So v double dot is simply x2 dot, and v dot equal to x2, and v equal to x1, and u is u. So this is equation 5, which is obtained from equation 3 in terms of state variables only. So from these equations 4 and 5, I can write this state equation. So x1 dot equal to x2 and x2 dot equal to minus 5x1 minus x2 plus u. Okay, so this is your x dot equal to x plus bu. So that is your matrix A, this is matrix B. Now I have to write the output equation, I mean y equation. So consider this first part, I mean the numerator polynomial which we have separated with this y. So again doing the cross multiplication, taking Laplace inverse. So Laplace inverse of it, that is y, svs means v dot plus 3vs means 3v. Now you have to write this, convert this equation into the state variables only. So y equal to, what is v dot? V dot we have already assumed to be x2 and v is equal to x1. So this equation is now totally in the state state variables. So this can be written in the matrix form like this. So obviously the equation 6 is rewritten like this: y equal to 3x1 plus x2. Okay, so it's the same equation. So that is your yx plus du. So this is your C matrix and D is missing here. So this is how you can convert your transfer function which has the numerator polynomial by this way. So I have considered the basics of the state space modeling, its comparison with the classical theory, its advantage, and the modeling of various physical systems, and then interconversion, I mean the state space to transfer function to state space. Now let's come to the MATLAB. Let's see what can I do in the MATLAB. So consider this example of state space model of an LTI system. It's the same, these are same ABCD matrices which we have just obtained in the previous case. So A, B, C and D. Now my objective is that I would like to create a state space model in the MATLAB, and I would like to do some basic analysis such as step response, frequency response, Nyquist, root locus, like this. So this is the simple MATLAB program, very simple. So here first you have to enter all the 4 matrices in the MATLAB, these 4 matrices, and now with help of this SS function. So in SS function, that is actually the state space. You have to pass all these ABCD matrices like this. So when this is executed, your sys state space model is created. So sys is your state space model. Okay. Now I have used this function SS to TF. What is it? Its name is very clear, SS to TF. That means I am converting this state space into equivalent transfer function. So I have passed all these ABCD matrices here. So when this executed, you will get your corresponding transfer function. So the numerator polynomial and the denominator polynomial will go into the num and tanh. So with help of this num and tanh, I am creating this transfer function with help of this TF function. So sys1 will carry the transfer function model. So sys1 is carrying actually your transfer function, while the sys is carrying your state space model. Okay, so I have both the representation of the same system, and now with these commands I'm actually having the various responses, such as step sys. Sys is your state space model. So by executing it, I will get the step response of this state space model. And similarly Bode sys, it means I will get the frequency response, Bode plot, root locus and the Nyquist of that state space model. Although I have created this sys model, if you do not create it, you can directly pass the ABCD matrices in these functions also. I mean the step, Bode, root locus, like that. So you can write a step, you can write A, B, C, D like that also. So you will get the same response. So now let me run this program into the MATLAB and I can show you that what type of outputs I can achieve. So let me jump to the MATLAB. So this is my MATLAB editor and this program is already written. So I will press the run button and let's see what I will achieve. So this program is executed. Okay, so I achieved all the analysis of this state space model. So you can see that this is the step response. Okay, this is the Bode diagram, I mean the magnitude versus frequency, phase versus frequency. This is the root locus. You can see it has the 2 poles and 1 0. So one pole is ending at this 0 and another pole is going to the infinity in search of 0. So that is the root locus, and this is the Nyquist. Okay, so this is how you can achieve all these analysis of this state space representation. So I hope you have enjoyed this session, and now you have the basic ideas of the state space modeling of physical systems, what is actually the state space and how it actually differs from the classical approach of the transfer function. Okay, so I thank you all very much for watching this video and sparing your precious time. Goodbye.